Robotic rovers have been exploring the Mars and the Moon since 1970. They traverse and explore extraterrestrial terrain hundreds of millions of miles from Earth. They must execute their decade-long missions without the option of repairs in case of failing components. This includes their locomotion system, which must move the rover, some weighing over a ton, over all different types of terrain. They also must withstand the hostile environments of other planets. Mars has temperatures between negative 153 degrees Celsius and 20 degrees Celsius. And they must do this reliably for their whole mission without breaking down or getting stuck. So how do these locomotion systems work? What would be some other methods of travel, and how do they compare? The most known locomotion type for a rover, and the one primarily used for exploration currently, are wheeled vehicles. Wheels are a very mature technology, giving it reliability while being mechanically simple and easy to control. Their main downside is their limitations climbing slopes, traversing sands, and navigating rough terrain. Tracked vehicles keep a high amount of traction even on soft ground, which lessens the chances of getting stuck. However, they come with increased mechanical complexity and higher power requirements. A more novel locomotion type is body articulation. Here the rover moves by moving whole parts of its chassis, for example similar to a snake. This allows for a large amount of terrain adaptability. However, it is mechanically very complex and currently only researched as a future option. Similarly, light robots are still in research, but promising in terms of capabilities. Legs allow for great terrain traversing ability, including climbing over obstacles. Lastly, there's the option of non-contact locomotion. This mainly includes flying robots using rotors or turbines to create a lifting force. Wheeled vehicles on Earth usually have 4 wheels because it is the best compromise between stability and mechanical efficiency. However, this is not the case for rovers on other planets, as the terrain and mechanical and power requirements are vastly different from those for cars on Earth. For planetary rovers, the agreed upon optimal number of wheels is 6. Using more wheels means that each wheel requires lower motor torque, reducing mechanical stress on other components. This also improves the vehicle's ability to negotiate obstacles. Theoretically, even more wheels could improve performance even further. However, the improvement is marginal and does not justify the increased weight or additional complexity. Traditional spring suspension systems are not used because they can reduce traction during climbing. When a wheel climbs over an obstacle, the spring is deflected, producing an upward motion that reduces the traction of the other wheels. To prevent this, non-spring-based suspension systems are used for planetary explorations. The most common such system is the rocker bogie assembly, first developed through the Rocky series of prototype micro-rovers by the United States. This system connects 6 wheels, 3 on each side, using pivotal metal rods to the rover body. It ensures equal pressure on all wheels, even on uneven terrain, enabling better traction. The rocker is connected to the front wheel and the bogie, and has a constraint of 16 degrees. The other 2 wheels are connected to the bogie itself. The bogie joint has a 30-degree limit, which allows for significant wheel movement. The differential connects the left and right rockers to the rover body by a pivot in the center of the rover's top deck. Steering the corner wheels enables for double Ackermann steering, which allows for up to 90 degrees turns. Together, this system allows the rover to negotiate step heights of up to 1.5 times the wheel diameter and cross crevices of up to 40% of the vehicle length. The construction of the wheels themselves is also incredibly important. They have to survive their year-long missions, support the rover's weight, and keep traction on different types of terrain. To give some insights into the complexity of rover wheels, I called my friend Jackie.
Hi, I'm Jacqueline Ryan. I work at NASA JPL on the Mars Perseverance rover, and previously I worked on the Mars Curiosity rover as a camera operator of the engineering cameras. The rovers that I'll speak on are primarily Spirit and Opportunity and Curiosity and the Perseverance rover, which is currently operating on Mars. So in the first, or really the second generation Spirit and Opportunity rovers, the wheels were smaller and solid and had a wave tread pattern. And the treads were very robust when driving over hard terrain, such as bedrock and outcrop, but they became easily stuck in sandy environments. And that was a consistent problem for both Spirit and Opportunity throughout the lifespan of their missions. Spirit, of course, famously got stuck in a sand dune in 2010. And Opportunity, similarly in its mission, at one point was stuck in a sand dune. And it was able to get out, but only after a significant amount of anomaly response from the operation team. So taking those lessons learned, the robotics team at JPL went back to the drawing board for Curiosity in terms of the wheel design. And the parameters that they had, or that they were expecting, was that Gale Crater would be a largely sandy environment, because with Spirit and Opportunity, they were expecting to see lots of large, hard pieces of bedrock that they would need to traverse. And in reality, most of the terrain that they were traveling over was very benign, flat, and sandy. So with Curiosity, they designed the wheels to be much better at handling sand. And to do that, they designed a new tread pattern. And the tread pattern is primarily composed of these things called grousers, which you can see my hands are making this formation here. It's rigid metal extrusions from the main body of the wheel that allow the rover to have traction as it traverses over any type of terrain, especially soft terrain. So to reduce the weight as much as possible, these wheels were made incredibly thin. And it was believed to not be as much of a concern to have wheels that thin, because the gravity is about 1/3 of what we have on Earth. And so it was thought that the stresses that the wheels would be under would not be as great. Now, the way that it actually worked out is Gale Crater was incredibly rocky and is filled with outcrops and sharp terrain features throughout. For the first period of the mission, mobility operations proceeded as normal, but eventually was noted through wheel imaging. And our wheel imaging can be taken either with the nav cams, has cams, or with the MOLLE camera, which is the ARM-based camera. Mostly we take it with the ARM camera. It was noted that the wheels had holes in them, especially in the wheel body. And this was somewhat unexpected. Obviously, the wheels had been designed to be very thin, but the level of degradation was somewhat anomalous. And so new mobility techniques needed to be developed. In particular, the mission became much more cautious to avoid large terrain hazards in the ensuing sols. And now we're fastly approaching the Geddes Vallis, and the terrain is not getting any easier to traverse, but the techniques for driving through it have. And so preserving the wheels has gotten a lot easier over time, just through better operational techniques. Still, given all of this, lessons were learned from the Curiosity wheels. And when designing Perseverance, the wheel design was changed again. So one of the characteristics of Perseverance's wheels is that they're slightly thicker than the Curiosity wheels. The other thing is that the tread pattern was redesigned again. And so this tread pattern returns to something more similar to Spirit and Opportunity's wave pattern, but still in the form of those ridges extruded from the main body of the wheel. And it's a hollow wheel like Curiosity still. Thus far in the mission, Perseverance has not encountered any significant wheel degradation, despite encountering terrain that has often just as many hazards as what Curiosity has encountered. This new generation of rover is much more capable at traversing through sandy terrain, although it's still something that we do try to avoid in our operations.
You said Perseverance had a lot less damage to the wheels over a lifetime so far. Is that mostly, do you think that's mostly because of the improved wheel design or because of the improved path planning and what you've learned from Curiosity and the previous rovers from avoiding obstacles that would damage the wheels?
I think it's a bit of both, but definitely the improved wheel design has greatly helped in reducing damage to the wheels through the Perseverance mission. And so, yeah, I would definitely say that's a huge contributing factor.
This seems like a very matured technology. Do you think is NASA still looking into other like systems, or are they happy with the rocker bogie and just are gonna be stuck with that for the foreseeable future?
Yeah, so it's my impression that there's no intention to change to a different type of suspension in future robotic missions. One of the things that's very important when designing a mission is the concept of heritage. And heritage is when we have something that worked on a previous mission. We know it worked well. We're going to do that thing again. And if we're going to do it exactly the same, as in the hardware will be exactly the same, it's called build to print. So certain components of the Curiosity rover and the Perseverance rover are build to print heritage from each other, meaning that a system that was proven to work well on Curiosity was copied over exactly as is and reproduced on the Perseverance rover. In the case of something like a suspension system, if it hasn't been causing any issues, we're going to continue using that system into the foreseeable future.
Tracked vehicles have a high ground contact area, leading to good traction on soft soil and are thus great for off-road applications. The main component of a track drive is the tread. It is what is contacting the ground and moving the rover forward. One or more driver sockets are what is transferring the motion from the motor to the tread. If a main wheel is not transferring motion, it is an idler wheel. Optionally, the tread is supported by bogie wheels, helping reduce ground pressure on the system. There are two approaches to transferring the motion from the driver socket to the tread. A friction drive relies on the friction between the driver wheel and the track. This requires the tread to be under a lot of tension to successfully work. The more common approach is using a positive track drive. Sprocket teeth in the drive wheels engage holes or complementary teeth on the inner surface of the tread. This system does not require the same tension on the treads. It is, however, susceptible to wear on the sprocket teeth. Vehicles with treads do not steer like wheeled vehicles by turning their wheels. Instead, they employ skid steering and drive their tracks differentially. This method relies on the slipping of the tracks leading to odometry being problematic. While this is not optimal in most rover applications, it would not be a major issue as wheel odometry is inadequate anyways and needs to be augmented using external modalities anyways. So, if tracked vehicles are better at traversing sandy terrains, why are they not used in current robotic missions?
So the problem with tracked vehicles is primarily that they present more points of failure as compared with wheeled vehicles. So not only do they have wheels, but they also have the track that goes around the wheels. And all of these items also add weight. And the combination of that creates a system that can be more difficult to maintain, especially in an environment where you don't have any ability to repair components of the rover. And so that's generally why I would say wheeled vehicles have been pursued for planetary environments.
The way current wheeled rovers are designed, some parts can even fail without stranding the rover in one place.
So on Opportunity, one of the steering actuators got stuck. I forget which wheel it was on, but basically one of the steering actuators was stuck and the wheel could no longer be turned. And the rover was still able to drive, albeit very slowly, because first of all, the drive actuator worked, and the other wheels were able to push the stuck wheel, even if it was not moving in the direction that the rover necessarily was steering in. So that's another characteristic of wheeled rovers that's great, is even if you have a faulty steering actuator, you're still able to continue driving. In a tread-based rover, I think if one of the actuators were to fail, it would create more significant problems in the motion of the tread system.
Another strategy to increase traction on uneven terrain is using an articulated chassis. This means the chassis deforms to fit the wheels onto the terrain with an even pressure. The concept of an articulated chassis is not a new one. In fact, it had already been built into a rover by the Soviet Union. Mazokot was supposed to explore Mars in 1996, but sadly it never set off on its mission after the Soviet Union fell. In this video, you can see the finished Mazokot being tested. Note how the chassis is separated in 3 large pieces that are connected with rotational joints and turned to move over the obstacle. The large wheels on the underside of the rover prevent it getting stuck while driving over the obstacles. While an articulated chassis brings the advantage of better traction, it has the cost of added mechanical complexity and a higher power consumption. Another feature that articulated chassis can enable is wheel walking. It is the strategy of moving the wheels to climb high-angle slopes or getting unstacked from fine sand. The Rosalind Franklin rover by ESA is supposed to be the first deployed rover that uses an articulated chassis. Originally planned to fly as a collaboration between ESA and Roscosmos, it is now planned to be launched in cooperation with NASA in 2028. Here you can see the Rosalind Franklin rover demonstrating wheel walking to traverse fine sand. For this, it locks some wheels while moving the rest forward using the articulated wheel levers and using the locked wheels as a leverage. This is repeated until all wheels are moved forward, and then the rover locks the wheels again and moves its body forward. Repeating this over and over, the rover can slowly crawl through the sand. All of these locomotion techniques focus on optimizing the traction to move over obstacles. Non-contact-based locomotion is avoiding obstacles completely by moving over them. This has only recently been achieved for the first time using the Ingenuity helicopter on Mars. There are some other non-contact-based locomotion types, such as planes and multi-rotor drones. All of these use aerodynamics to generate lift, meaning they require an atmosphere to work. This can be problematic on planets such as Mars with a very low density atmosphere. The robot must compensate for this by being lighter, having larger lifting surfaces, and spinning its motors faster. While all of this makes powered flight incredibly hard to achieve, it brings a lot of advantages for exploration.
The greatest advantage to using a helicopter as opposed to a rover is that you don't really have to worry about large terrain features that would not normally be traversable. A great example of that would be like there was a dune field in Gale Crater that Curiosity needed to traverse back in 2017. And luckily, there happened to be an area of exposed bedrock in a narrow strip in the middle of this dune field that we were able to traverse relatively easily. But if we had had to drive over the dune field, it would have been much more difficult, if not impossible, to get further up Mount Sharp. With a helicopter, you don't have to wait for lucky breaks in the terrain to get over a dune field. With a helicopter, the advantage is that, for instance, I could fly from one butte to another as long as I were safe to land on both. With a rover, that would be totally out of the question because it probably couldn't drive up the slope, or it would take too long. It would take, potentially months to go between two buttes that are even maybe next to each other, only 50 meters apart. But for a rover, that can be worlds away because of the slope limitations and the slip limitations. And with a helicopter, you can just fly from one to the other. So that's a great advantage.
In the past, we've only seen wheeled rovers be used for exploration. The first successfully deployed rover was Lunapod 1 in 1970. It, and all the rovers deployed since, have used some type of wheel-based locomotion. This includes all the US Mars rovers, which have all used the rocker bogie suspension. Spirit and Opportunity in 2003, Curiosity in 2011, and Perseverance in 2020. The Mars 2020 mission also included the Ingenuity helicopter, which executed the first powered flight on another planet. The Rosalind Franklin rover by ESA is planned to launch in 2028 and will be the first rover to use an articulated chassis. Another very exciting future mission is the Mars Sample Return mission. In this mission, samples of the Martian soil that have been taken by Perseverance and then dropped onto the surface are supposed to be returned to Earth for further research.
It's currently proposed to include 2 sample retrieval helicopters or sample recovery helicopters, which we're calling SRH, in the Mars Sample Return mission, which is being developed by JPL. And a lot of the design for these helicopters is coming from the successes of the Ingenuity helicopter.
It seems that near-term planetary exploration missions will rely on wheel-based rovers and helicopters. However, with manned missions to the Moon and later Mars planned, repairs on rovers won't be impossible anymore. When a single drive system fault does not risk a complete mission failure, the better mobility of tracked or legged rovers may make them a better option than wheeled rovers at that point. As technology advances and our capacity for interplanetary travel and exploration grows, we may see a wider variety of locomotion techniques being employed to uncover the mysteries of our solar system and beyond.